Okay, so for 1.2, once we see the graphical symmetry along with how it relates algebraically, I think we'll be in pretty good shape here. So if we look at number 1 here, y equals x squared is symmetrical to the blank. Let's go ahead and just take a look at it graphically. As we know, y equals x squared, we just do an input-output table for it. It would give us a nice neat parabola. And symmetry means that a reflection or same distance from a line or a point in the opposite direction. Meaning, if I take, let's say, a point like right here, its distance from the y-axis, if we go in the exact opposite direction, and we get a corresponding point, and we do that at every single point, therefore, that's symmetry, and therefore, the parabola is symmetrical to the y-axis. So y-axis. And algebraically, what x values will give you the same y values. So if we look here, like y equals x squared, we can do this as a coordinate. If we as input-output, for instance, if we plug in 2, 2 squared would give us 4. And we also know that if we plug in -2, that's inside parentheses, so squared also gives us 4. So we see that opposite x values give us the same y value. So that being said, if we have a general point xy in the graph, sorry, can't fit it in there, I'm just going to write below, that means the opposite of x will produce the same y. So algebraically speaking, that's how we can easily test if a point is, if a equation is symmetrical to the y-axis rather than having to graph it. So, that being said, in order to determine symmetry to the, sorry, can't fit that in there, y-axis, we replace x with -x, and then that will give us an equivalent equation. We'll see what that means. Long story short, it means we plug in x, simplify, like if it's squared, for instance, or I think I said that right. If we plug in -x, we plug that in, square it, the negative goes away, and the result, after simplifying, if that's the same equation as what we originally had, then we know the equation, that equation would produce a graph that's symmetrical to the y-axis. Okay, so now if we look at y squared equals x, typically you're used to solving for y. If we did solve for y, we square root, we'd also get a plus or minus root x. So that means graphically, and of course we could do an input-output table for that, graphically we would get a positive root x and a negative root x. It's supposed to be at the origin right there. Another way of thinking it, if you look at the relationship between y equals x squared and y squared equals x, the y equals x squared is a parabola about the y-axis, therefore it's reasonable that y squared equals x is a parabola about the x-axis. So if we look at this, that symmetry is going to be about the x-axis in this case. So our symmetry is about the x-axis. Algebraically, what values give you the same x values? Well, if negative x will produce the same y value as positive x in the first one, then we would assume or easily predict that x comma negative y would give us the same. And of course, if we look at an input-output table, let's say if we have 0 for, how about we do it this way? Let's go input-output table where we plug in for y. So if I plug in 0 for y, I get 0 for x. Remember, I'm just plugging into there right there. If I plugged in 2 for y, I would get 4 for x. Also, if I plugged in -2 for y, that would be squared and turn positive 4 for x. So we see that opposite outputs give us the same input. So, that being said, sorry this is getting a little messier than I wanted, but hopefully you're following along well enough. If x, so I am right here. If xy is on the graph, then x negative y is on the graph. Therefore, to determine symmetry to the x-axis, we are going to replace negative y with x. and it will produce an equivalent equation. Okay, coming down to number 3, y equals x squared. If we graph that, again, if we just did an input-output table from like -2 to +2, we get a graph that looks like that. And here, our symmetry, if we take any point, it's not symmetrical to the y-axis. Obviously, we don't produce a equivalent point on the same distance opposite over the y-axis, same with the x. But if we combine the two over the x-axis and over the y, or I'll do that in a different color, if we went over the x and over the y, or more accurately speaking, through the origin. The origin is our point of symmetry. And we can continue looking at that with all points on the graph. So I'm just going to write 0, 0 here. And so algebraically, as we see, for instance, we could go back over here. If I did an input-output table, I'll just do a couple. 2 into x, 2 cubed would give us 8. If I plugged in -2, that would give us -8. So opposite x values give you opposite y values. So algebraically, -x gives you the opposite y values and vice versa. Therefore, if we have, so right here, therefore, to determine the symmetry to the origin, we are replacing x with -x and y with -y to give you an equivalent equation. So what does that look like algebraically? So if I look at here, I'm going to do my first test by plugging in -x to test symmetry to the y-axis. In this case, we see -x squared would just turn back positive, and after we plugged in -x, we had an equivalent equation, and therefore symmetrical. Therefore, those 3 dots is the symbol for therefore. Symmetrical to y-axis. I may have said x-axis in there, but that is the answer. It's symmetrical to y-axis. We could eyeball, just kind of like look at if we plugged in -y and -x and -y and see if it's symmetrical to the other. So if we plugged in -y, we'd have the opposite of -y, which turned positive. So we had 3x squared plus y equals 0. And that obviously is not the same as the original, so it's not symmetrical to the x-axis. And same thing would happen if we plugged in -x and -y. The -x squared would turn positive, and opposite of -y would turn positive as well, so it would not produce the equivalent equation. So we're just symmetrical to the y-axis there. Okay, let's take a look at this one. If I plug in -x, opposite of x, or the opposite of x quantity cubed would 3 negatives obviously turns negative or stays negative, and therefore that's what happens when we plug in -x alone, and this equation is not the same as that, therefore it's not symmetrical to the y-axis. What if we plugged in -y? Hopefully you'll see before me going through this what's going to happen. -y, we just move the negative out front, and that obviously is not symmetrical to the x-axis because this equation is not the same, is not an equivalent equation to that. And then if we do our last test of negative in both, well, we saw that this would produce a -x, this would produce a -y. So if we move both those negatives out front, that turns positive. So we have an equivalent equation here. So we plug in -x and -y, and we produce the equivalent equation to the original, and therefore symmetrical to the origin. Now, this is not going to be moving to here is not going to be something that is going to be utilized often, but just FYI in terms of some of these on your homework. One way we can do this is produce an input-output table. We could also use our transformation rules. If we do produce an input-output table, I'll go ahead and go through that. So the first x value that would produce 0, this is how I like going about roots, or root function or root equation. I like, because square roots are, we want to find perfect square inputs, I pick my outputs as 0, 1, 2, and I say, okay, well, what x value would I have to substitute in order to get that y value? Well, if I substitute in -5 here, that would give us 0, so that would be -5. To get the next one of 1, I need, what value of x do I need to get out 1, and that would be -4. And then, because the square root of 1 is 1, what value for x would I need to get out 2? Well, in order to get 2, you need to square root 4. So what value would I have to plug in for x in order to get 4 underneath the radical? That would be -1, because -5 plus 4 is, -1 plus 5 is 4, and the square root of 4 is 2. Now if I go ahead and graph that, let's see, I zoom in here. -5, 0, 1, 2, 3, 4, 5, -4, 1, and -1, 2. If we look here, that's our entire graph. There is no symmetry there. So it's not symmetrical to the y-axis, x-axis, or the origin. For this last one right here, I'm going to, I think it'd be best to choose outputs again. So I'm going to go 0, 1, 2. And if I pick 0 for y, that would leave us with an x value of 1, because 0 squared plus 1 is 1. If I plug in 1 for y, that'd be 1 squared is 1, 1 plus 1 is 2. Now if I plug 2 in, that'd be 2 squared is 4, 4 plus 1 is 5. If I graph those, 1, 0, 2, 1, and then 1, 2, 3, 4, 5, 2, looks like this. Now you look at this and you go, well, that looks like the other graph, which wasn't symmetrical. But the if I did my let me go back to this really quick. If I go over here and I try my symmetry test of -x, -y, and then -x and -y at the same time, none of them would work. So given the fact that if we did our symmetry tests, we end up getting a graph that we know that's the complete part of the graph. It's not like we missed anything, and the symmetry test didn't reveal selection of inputs and or outputs that we didn't account for and miss part of the graph. So we know that that's all we have for the graph. Now that being said, over here we know if we do the symmetry test by plugging -x in, or excuse me, -y in for y, it would produce the same graph. And therefore, even though we produce this graph over here, we know this graph is symmetrical to the x-axis, and therefore we can, without even having to get any more input-output values, we can reflect it about the x-axis.